Let me start recording. So I think it's about time to start. And welcome everyone. Come to the third week of this year's Food and Logic Summer School. And in this week, we have invited Professor Antonio Montalban from UC Berkeley to give us a talk, 4 days talk on Scott complexity of countable structure. And in this week, we have a break on Wednesday, right? And for each day, we will start at 8 o'clock to 11 o'clock. Goes in Beijing time. Can you hear me?
Yeah.
Okay. We also have a half-hour break in the middle. Now let's welcome Professor Montalban.
All right. Thank you, Rudy. Did you pronounce that right? So I'd like to know, yeah, so my name is Antonio Montalban. So I'll be teaching this course for the next 4 days, 5 days. So I'd like to know a bit about the audience before we start. I guess so. Is that the standard in China? Like nobody has a camera on?
It's 8 o'clock.
Oh, yeah. So I'm asking. Yeah, it's good to speak, so we get used to my accent. Is it standard that nobody has the cameras on? So I have no idea what you guys know. So the most interactive we do it, I think it's better for the audience, because I'll be able to teach you something at the level you need. Because I could go all the way high up or all the way low down, but the best will be to get the level you guys want. Okay, so if you don't want to put the cameras on, if you're shy, maybe you can answer in the chat, like maybe something about your background. So how many students here are I don't know, undergrad students? I don't know how you say that. What's the equivalent in China?
多少人是本科生能够 How many 本科生 I see one raise. Okay.
And then okay, what about what else is there? Like master students are there, or PhD students? Is that? So a few more, I guess. Yeah, hands are up. Cool. And the rest, I don't know. What else? High school students?
I think there's no high school students.
Right. Cool. So what background can I assume you guys have? Like, so everybody took some logic classes, I assume. And Rishi, you said you guys look at my book some.
Only some of you have looked at it.
Some of the people here.
Yeah, most of them have learned at least one logic class, I guess.
Okay. So I mean, I could do it. I mean, I'm repeating this again because I think it's important that if we make it more interactive, it'll be much better. Because otherwise, I could just talk about anything, and then you won't learn much if you're not getting the audience on the right spot. So what my plan for today is going through those slides that I sent you, that you guys got in the email. I'm gonna go very slowly through the slides, and the slides gonna give an overview of the whole 4 classes essentially. And then if we have time today or starting tomorrow, we'll go deeper into some of the theorems mentioned in the slides, and we go into the proofs. And so the talks in the rest of the week, we're gonna be like just writing on the iPad. Okay, so the first day with slides, but then it's gonna be just writing like in a blackboard, but in the virtual blackboard. But as I go along today, I like to get comments about what things you guys know and you don't know, what things we should go deeper. Because as I was saying, I assume people have very different backgrounds. And then also the topics that we go deeper into, it's mostly whatever is you find interesting. I mean, I could be flexible, it's essentially. So there I have an ideas of what things I could go deeper, like we mentioned in the syllabus for the class. But it doesn't need to be that. We can do kind of whatever you guys find more interesting and exciting, and it's at the right level. And so the slides at the beginning kind of go towards the topic, but then the next few classes, we're just going deeper into many things. It's a way of teaching different notions in the area, like with a common goal, but you're teaching different notions. Okay, so that's the plan. Let me share my screen now. Oh, these are hands up. Do you guys have questions? Or is it, oh, no. Z, no question. It's one hand up. Okay, so I need to be able to share again. It tells I cannot share.
Cannot share? Oh, maybe I passed you the host of, then could you allow me to record? Since if I pass you the host, then I cannot record.
Co-host, you don't need to be host. Yeah, I don't
know how to set a co-host.
I think you can just allow me to share without making co-host. You can go.
I didn't see the option. Where can I find the option to allow sharing screen? I didn't see that.
Probably on my icon, either in the list of participants.
Oh, I see. Okay. Can you share now?
Let's see. Yes. Okay. Can anybody see that?
Yes. Yes.
Cool. I would say I don't see anybody's faces. Okay, so complexity of it's called complexity of countable structure. So in computability theory, so one of the areas that we study is this one, like complexity of structures. I guess in math, in logic, in general, we care about complexity. Computability theory has the tools to study countable things, right? Because computability theory works on complexity on the natural numbers. So we got the tools now to study complexity of anything at the level of countable, right? So if you want to go to uncountable and beyond, then you need to ask Sugao and the script set theorists to study the complexity of things that are uncountable. If you want to study complexity of finite things, maybe computer science and the problems about P and P, that's where you study. Computability is in the in-between, where we study countable objects. And usually this area is called computable structure theory, but we rarely look at, well, we look at computable structures, but non-computable too. The objective is to look at complexity. And one of these notions of complexity is due to Scott. And it's not really, it's somewhat related to computability, as you will see. And I'll tell you a bit about the history of this as we go along. Okay, so that we are all on the same, standing on the same step. So let me define what I mean by structure. I hope everybody knows this already, right? So a structure just consists of a set that we call the domain, on which we have constants, operations, and relations. Lucy, this is everybody's up with this?
Yes, I think everybody.
Yeah, so these are the, when I say structure, I'm going to be thinking of guys like this. So we have we have a domain where you take the elements from, we have a few constants, we have operations, and we have relations. Right, so when I say structure, that's what it means. Cool. I don't need to go further into that. Exit. And as you may imagine, some structures are more complicated than others, and we would like to measure this complexity before. Okay, so can we measure it? Can we measure how complicated that? How do we do it? Of course, there are many ways to do such a thing. We're gonna see one that is rather robust, which is this one on Scott track. Okay, but so we want to study the complexity of a structure. So a structure can be any of these. These are all actually quite simple, but we can find many more that are more complex. And we're gonna do this systematically. Like we're gonna look at 3 different aspects of the complexity of a structure. One way is gonna be what we call orbit complexity. I guess I call it that for the talk essentially. I don't know if it's used in general, but to organize the talk, I'm going to divide it like this. So orbit complexity, by orbit complexity, I mean that how complex are the automorphism orbits of a tuple. Okay, so 2 tuples in a structure are automorphic if there is an automorphism of a structure that maps one to the other. Right, so that's what it means for 2 tuples to be automorphic. And the automorphism orbits, so the automorphism orbits of a tuple is the set of all the other tuples that are automorphic to it. Yes, are we all good with this? So automorphism orbit. The automorphism orbit of a tuple A in a structure A is the set of all tuples B that belong to the same size, such that tuple B is automorphic to the tuple A. So structure A with the tuple A is isomorphic to the structure A with the tuple B. Right, so this means A and B automorphic. Right, there's an isomorphism that maps the structure A to itself and maps the tuple A to the tuple B. Yeah, everybody's good with this? Cool. And right, so the 2 structures, it's 2 tuples are automorphic. These tuples are essentially the same from a structural viewpoint. There is no way to differentiate them. But then we can look at the complexity of each orbit as a way of deciding how complex is the structure from the inside. Another way, another aspect of complexity that we're going to be looking at is this one that I call identification complexity. Okay, and this is, the question comes from how difficult is it to recognize one structure from the others? Okay, so so if I give you a structure and I want to know, is this structure, is it the one we want or is it a different one? So suppose we have a structure in mind and somebody gives me another one, and can I recognize that they are the same structure or can I recognize they are different? So that's what I mean, identification complexity. So I give you a representation of a structure and I want to know if it's a certain one that I want or if it's a different one. Okay, so it's the complexity of the structure from the viewpoint of differentiating it from others. Okay, so the first one is something that is kind of from within. You're looking at the difference of the tuples within the structure, and this one is from the outside. You're comparing the structures to other ones that are not isomorphic to it. Okay, so that's what I mean by identification complexity. It's going to become more clear once we start looking at particular definitions. The third aspect that we want to look at is how complex are isomorphisms between representations of the structures. Okay, so now here suppose you're given two representations of the same structures. They're the same structures, they should be isomorphic. It has to be an isomorphism. How difficult is it to find these isomorphisms once they give you the representation of the structure? Okay, and that's going to be another way of measuring the complexity of the structure. And the idea is to, again, as I said, in the next few classes, go more into details, into all these things, and go look at examples into more details. And more examples. But today we'll do a more of an overview. Okay, and so these are the three aspects of complexity we're going to look to measure the complexity, and we're going to use three tools to measure complexity that we're going to describe today from a general viewpoint. And they are the back and forth relations, the Borel-Baer complexity hierarchies, like in the distributed set theory, and the infinitary language. So these are three tools we're going to use. I like to spend probably maybe the end of today or tomorrow going more into infinitary formulas. Actually, maybe I spend quite a bit on infinitary formulas. I think it'll be good to spend some time, maybe Thursday, on back and forth relations, and then maybe Friday we go into these things, or we can see what else we are at and what we do on Friday. So back and forth relations are going to be used for this type of complexity. Baer-Borel complexity are going to be used for identification and isomorphism complexity, and infinitary formulas are going to be used for orbit and so an identification complexity. So in a way, we have kind of three tools, three aspects of complexity, and some combinations of them. We can kind of have 5 different ways to measure complexity of structures of same structure. The interesting thing, which is going to come out, and I'm going to have a longer theorem at the end of the talk, is that many of these ways of measuring complexity are equivalent. Actually, they are all equivalent. So here's the theorem. Don't worry if you understand what it says now, because we're going to go into the definition of all these terms little by little. Okay, so we're going to go through them. Should be easy enough. So yeah, so this is true for a successful ordinal. Suppose you have a countable structure A. So the following are equivalents. One is that the automorphism orbits are sigma alpha definable. One is that the set of representations of the structure A is pi alpha plus 1 in the Borel hierarchy. And the third one is that there is an isomorphism function that is Baer class alpha minus 1. Okay, so as I say, I didn't define any of these formulas, but I just to show you kind of the shape of the theorem we're going to be pointing at. And if you can look at the shape, this one is talking about automorphism orbits. So this is the orbit complexity. This one is talking about representations of a structure, all the things that are isomorphic to the structures. So that's isomorphism complexity. And this is an isomorphism function. So this is what we call identity. So this one is identification complexity, and this one is complexity of isomorphism. So these are the 3 different aspects of complexity, but we have these theorems that connect them all. So that studying the complexity of the 3 different aspects, we still get same notion of complexity, same rank. And we are going to call the rank of the structure to be the least alpha that satisfies any of these things, that they are all equivalent. So this rank alpha is an ordinal that is going to measure in some way the complexity of the structure A. So this rank is what I call the Robuster-Scott rank. So it's a version of the Scott rank. So the Scott rank was originally defined by Scott in 65, but his definition, the details of the definition were not really taken that seriously. So you can look at many other books and papers, and different people use different definitions of the Scott rank. And by different definition, I don't mean equivalent, but they just use different words. I mean, they give you a different number. They give you a different order, these definitions. Sometimes they are off by omega. They are not too far from each other, but they could be actually quite far from each other, the different definitions. So the Scott rank, when people refer to Scott rank, there's a bunch of definitions you can use, and there's an idea that has to do with it. And of course, there's the original definition of Scott rank, which that's the one that has a name, you would say. But depending on where and what you want to use it for, you might want one definition or another, which you get different ordinals. And for different structures, you might get the one is bigger than the other, or the other one is bigger than the one. It's a bit of a mess. But then for those definitions, for none of those definitions, you get such a nice theorem. So that's why I like that's what I say is good about my version of Scott rank, because you get the precise equivalence between all these different notions of complexity if you define the Scott rank this way. The way it's defined here, and we're gonna go into it that much. So it's robuster in the sense that you can look at it from very different angles and you get to the same value. Well, that's not the case for any of the other definitions the other ones use. I don't know which one Sugao uses in his book among all these. But as we'll see, this one has that advantage that they all equivalent. Any questions so far?
So what's this original definition based on? Are they all based on osmosis orbits or isomorphism functions? Or?
The original one is orbits. It's using these back and forth relations, and so is this one. They all of them are on, about orbits. All of them are about orbits, but then this is using back and forth relations, but not the ones that I defined here. This is a different one using back and forth relations. This one is using the infinitary language, but measuring complexity, not in the same way as I will measure it here. So yes, you get all different things. But yeah, orbit complexity, all of them. So right, so in the Scott rank, there was no, so so this was not used as a measure of complexity. It was kind of known that whatever value you get for alpha is in ballpark close to the Scott rank by a factor of omega, plus minus omega. But there was no theorem that says this is equal to that. And now we get a theorem that says this is equal to that. Other questions? No. Okay. So let's go on to the first technique, which is this back and forth relations. So today, just to give you, so that at least we can leave today understanding the statement of the theorem and some of the definitions, we'll go through most of these definitions in a bit of detail, but I'll go into much more detail, probably back and forth relations in the lecture on Thursday. Okay. So these back and forth relations, we use this version due to Ash and Knight, which follows the spirit of Scott's original definition, but it's not the same because Scott's original things don't fit that well, and in their version things fit much better. Okay, so and we want to measure this, and we want to measure the complexity of the automorphism orbits using these back and forth relations. Okay, so let's start with a structure. So we have a domain. We have some number of constant symbols, could be many, some operations, and some relations on the structure. Okay, and I'm always going to assume that the number of the vocabulary, the number of relations, constants, and operations is countable. Might be infinite, but if it's infinite, it's countable. And now I'll consider tuples, A bar and B bar. That's notation I use for finite tuples from the set A. And okay, so the idea for this back and forth relation, let me just start with the idea and then we define them formally. So given a number n, we're gonna define a different relation, a different back and forth relation for each number n. And actually we're gonna go through the ordinals, but let's start with the natural numbers. We're gonna define a relation less than or equal to sub n among tuples in the structure, which says that A looks like B up to level n, whatever that means. We're gonna explain that. Okay, so the larger the n, the more they should look alike. Okay, but the relation, if they are just by being related, it means that they look alike somewhat. So they could be non-related at all. We can none of them is less than or equal to the other, in which case they look very different. Well, or somewhat. So with that idea, we're going to define what we call the AK for Asian nights. So say define this version of rank. To be the least n, such that if the relation holds of a tuple A, B, then the tuple A and B are automorphic. Okay, so by the isomorphic there, I mean relative to A. So here I mean that the structure A with the tuple A bar is isomorphic to the structure A with the tuple A B bar. So there's an automorphism of the structure A that maps A bar to B bar. Okay, if there is an automorphism, if the two tuples are automorphic, they look super. They couldn't be more alike, right? If two tuples are automorphic, they are exactly alike. So in that case, you always get that this relation should hold, right? Because this relation is trying to measure how much they look alike. So if they are automorphic, this is always going to be the case. And the larger the n, the closer you're getting to saying they're actually more alike and more alike. So the idea is that the rank is going to be the least n, such that when this relation holds is because they actually are automorphic. They are as alike as they could ever be.
Do you mean for every tube AB?
For every AB, yes. Let's write that down. So for every AB. That's not the that's one definition. It's not the best definition we're gonna use, but that's the idea. Okay. So the larger the n, the more they are saying these tuples look alike, and we're gonna find the point when actually saying that they are related means they are automorphic. Okay, so let's now go into the definition of these back and forth relations. And again, I'm gonna repeat this when we use it later, but at least let's get a definition so you can give an idea of the notion. Okay, so we say that a tuple A is zero equivalent or zero related to a tuple B if they generate isomorphic structures with an isomorphism that matches A and B. Okay, so what are we saying here? So we have these two tuples A and B. Let's write it down. So we have here is the structure A, and here is the structure A again. And here is the tuple A bar, and here is the tuple B bar. And we apply the functions and the constants, and they kind of generate some little structure that is just generated by applying the functions, the operations on them. And we're saying that they are zero equivalent if there is an isomorphism mapping just the structures that they generate and mapping A to B. So you can map A to B, and then this guy is isomorphic to this guy. Okay.
Usually it's finite extension.
Yeah, usually it's finite extension. I'm not. Yeah, that is true.
Must it be proper extension?
Say that again.
Must it be proper extension? I mean, you really get more involving more elements. It's proper extension.
Yeah, I'm involving more elements. That's because I don't want to get into the technicalities yet. So this definition works the same. Once you go past one, this definition is the same as the one in the book. Let's say for the zero level, this one I'm giving here is not exactly the same as the one in the book because of what you're saying, because you only look at finite dimensional stuff. But let's not get into those details for now. Okay. Or if you want, we can make a structure relational, and then consider just that. But let's stay with this is not the definition I have, but let's stay with this just to start. So okay, so the structures, but then we don't say anything about the rest of the structure A. Okay, so that's what it means that it's two tuples are isomorphic. So essentially you're saying all the quantifier-free formulas about A are true about B and vice versa. That's what this is saying. They satisfy the same quantifier-free tuples. And now we're going to start defining the next level up. So the next level up, we are going to say that a tuple A is below a tuple B. And okay, this is our screen. We have A, here you have a copy of A. Here is A bar, and here is B bar. If for every B in here, let's call it, there's an extension of this tuple D, there is an extension of this tuple C, such that now these tuple together are zero equivalent. Okay, that's less than or equal 1. So whenever I can extend on the B side, I can find a matching tuple on the A side such that they are like this. Okay, this is not symmetric anymore. Cool, so far so good. Let's look at same thing. Let's look at examples. That's the only way to so I'm writing the definition here again, so we can use it in the examples. Let's consider just a structure that consists of the rationals and the order on the rationals. Okay, this is the simplest structure we can consider, I guess. So this is what happens. Two tuples are zero equivalent if the order among the elements of the tuple are the same. Okay, so like for instance, we suppose that in this tuple A1 up to AK, we know that A2 is less than A1, which is less than A5, which is equal to A4, which is less than A3. Suppose that's what's happening with this tuple up here. I mean, they could be in any order, right? It's a tuple of elements of the rationals. They could be in any order. So to be equivalent, we will need that this one satisfies the same thing. B2 less than B1 less than B5 equals B4 less than B3. If we have that, then they are zero equivalent because we can find an automorphism of a structure that maps one to the other, right? So if we have here the rationals, and here's the rationals again, and here we have A2, A1, A5, which is equal to A4, and here is A3, and here we have different rationals, but it's somewhere here is B2, and right next to it is B1, and up here is B5, which is equal to B4, and up here is A3. They are in the same order. That's what we are assuming. That's what this says, that the order among them is the same. Then we can match them in a way that, yeah, of course, the structure they generate, I mean, there is no relation, so they just generate themselves, right? There is no, when the structure generated by them is like nothing else, right? And being isomorphic means that you can match them one by one. And here, the only relation is the order, so you have to say they are in the same order. Yeah? Everybody's good with this? I'll take the silence as a yes. And this is the same thing as saying that they are automorphic, right? Because if we want to match the tuples, I don't know if you guys know the Cantor's theorem that whenever we have two dense linear ordinals, they are isomorphic. You can map this interval up here in an isomorphic way to the corresponding interval up here. And you can map this interval up here in an isomorphic way to this interval up here. And you can map each interval to the corresponding intervals, and you can get an automorphism of the rationals that maps one tuple to the other. Yeah, so in this case, being zero equivalent is the same thing as being automorphic. Cool. So then that's the end of the story. Once your relation just tells you you're automorphic, that's the end of the story. And according to the idea that we define, we say that the way we want to define the rank is going to be zero, because at zero level, you already got that zero relation is the same as automorphism. Cool. Let's consider now the integers with the order. So in this case, the zero relation is the same, right? The structure they generate, these tuples is themselves, they don't generate anything extra because there is no functions or operations or constants. So they are isomorphic if and only if the ordering among them is the same, right? The ordering among the elements of the tuple is the same. But now this is not the same as being isomorphic, right? Because, for instance, we have like the tuple, let's say the tuple -1, 3, and the tuple 1, 2. They are equivalent at level 0 because they are in the same order. The first element is less than the second element, right? So A1 less than A2 and B1 less than B2. So they are 0 equivalent, but they are not automorphic, right? You cannot map the integers to themselves and map -1 to 1. So if you have the integers here and the integers here, and here you have -1 and 3, and here you have 1 and 2, there is no way to map them and get and extend it to an automorphism of the integers, because you have these two elements in between. that you don't know where to map. Okay, so in this case, this is not equivalent to them being automorphic. Okay, so zero equivalent doesn't mean automorphic. What about less than or equal 1? So let's just do it for the case when we have only 2 elements. But just to simplify the situation. Okay, so here's the definition of less than or equal to 1. And it says for every extension of this tuple, we can find an extension of this tuple that matches it. Okay, so how are we going to extend this tuple? So essentially, what we have here is, so let's say here we have B1 and here we have B2, and we are inside the integers. And here we have the integers again. And now we have A1 and A2. Now I want to look at any extension of the tuple B. So the extension B is going to come from here. I'm going to have like some element here, some element here, and some element here. Right? These are my D's. My D's are going to come from all over the place. And I need to find the C that matches it. So I need to find the C's right here, and right here to be in the same order. That's extend the tuple C. And to be able to do that, what do I need? Like if I chose 4 elements here, I need to be able to choose 4 elements in between A1 and A2. If I chose 5 elements here, I can always find 5 elements to the right, 5 elements here. I can always find 5 elements to the left because there are infinitely many. The important thing is that there are enough in between A1 and A2 to match how many I chose between B1 and B2. So you can work it out. So these two things are less than or equal 1. If and only if they are 0 related, you need that, of course. And the interval between A1 and A2 is greater than or equal to the interval between B1 and B2. Right? Because this tells you that doesn't matter how many things I chose in between these two, I can find enough elements in between these two to match them, just because the interval is larger. Okay, the interval between A's is larger than the interval between the B's. Cool. This still doesn't imply that the tuples are automorphic. Because, I mean, to be automorphic, you need to have the same, the intervals have to be the same between the tuples, right? Between the elements of the tuple. And in this case, this one, all we are saying is that it's larger than or equal, but not equal, not necessarily equal. So then we can define what we know, what we can do. What happens is that these structures are automorphic if and only if they are one back and forth related in both directions. A is less than B and B is less than A.
So Antonio, and it's less equal or greater equal. I mean, A2 minus A1, less equal or greater equal.
You mean here?
Yeah.
Yeah, it's greater than or equal. Yeah, it's the opposite of what this one is. Because you want to be able, so there's these on the B side. So for every extension.
Oh, yeah, right. Yeah, okay.
You want for every extension on this side, on the B side, to be able to match on the left. So the left has to be bigger. You have to have more room on the left.
Right.
So it's the opposite, yeah. But if you're back and forth related less than or equal and greater than or equal, then the intervals are going to be the same size. And if the intervals are the same size, then you get that the tuples are automorphic. And you get that the rank that the idea that we were defining before, you get 2. Because at the next level, you're gonna get that less than or equal to is the same as automorphism. So 0 didn't work, 1 didn't work, but 2 is gonna work. But this is the Asian Knight rank. So we can keep on going. You can imagine how this keeps on going. The definition is the same. So you say A is less than or equal to than B, and the definition is the same. For every tuple that extends B, there is a tuple that extends A, such that AC is greater than or equal BD. And the back and forth comes because we are doing, so here we have less than or equal, and then we switch to greater than or equal. That's the way these things go, and that's the way they work well to match all the other theorems, all the complexity in the other different ways. Okay. So that's the definition at the level 2. And then we can keep on going. At n+1, we say A is less than n+1 than B. If for every extension on the B side, we can find an extension on the A side, such that you're greater than in the n level. Okay, so the higher this relation is, the higher the n, the more inside these tuples you're looking. Inside the tuple, the structures, they whatever they define, how they actually look. So the isomorph, the structure they generate is not enough to tell automorphism. Then you look at the extensions, and then you get this relation. But then you look at extensions, the extensions, and then you keep on kind of looking deeper into the structure of these tuples. And being related means that they behave more and more alike. And then we can keep on going through the ordinals. So then we can say A is less than omega B if for every n in the natural numbers, A is less n than B. Okay. How and then we can keep on going. A omega plus less omega plus 1B. If for every extension of B, there is an extension of A, so you get the omega relation now. How are and dot dot dot? How are we doing with ordinals? Luigi, I have one slide about ordinals. Maybe you can tell me if everybody knows this already, or
I think most of the audience should know definition.
Should we just do a quick definition then, or?
I think it's okay. Just assume they know about this countable ordinal.
Okay, so I'll just keep my slide on ordinals then. Excellent. If not, chapter 1 on the book is on ordinals. Very quick. I mean, it doesn't assume, it assumes kind of you know a little bit about the ordinals, but it's a quick chapter on ordinals. If you want a refresher, you could look at that. Okay, so we are again defining this zero equivalence, and now we can define the alpha equivalent right away. So now alpha is an ordinal, a countable ordinal, and we'll define A less than or equal alpha than B. If for every beta less than alpha, for every tuple that extends B bar, there is a tuple that extends A bar, such that we get the relation for beta. Okay. So when alpha is a limit successor ordinal, you might as well consider the only beta that matters is alpha minus 1. So in the case of, like, let's say A less than or equal alpha plus 1, B, the definition above is equivalent to saying that for every D there exists a C such that A, C is greater than or equal to alpha BD. So in the successor case, the two definitions are the same, but in the limit case is that you need to consider all betas below alpha, because there is no previous one. So for each beta below alpha, and for each D, you find a C where you get the matching partition at level beta. But different betas, for different betas that are closer to alpha, in the limit case, you might need different C's that are closer to it, not always the same. Okay, more or less, we're going to be looking at, again, examples in 2 classes. So Scott defined back and forth relations in his paper in the 60s, 65, I guess. That's he didn't use this notion of back and forth. He used one that is somewhat similar. It's asymmetric. I guess he used tuples. He used singletons here. There were a few technical differences in the one that Scott used, but it was more or less defining these back and forth relations, and that's why I started, because it's kind of the closest to the original definition. And then he shows, okay, that I guess you have to say for every structure. So given a structure A, there exists an ordinal alpha that's going to depend on the structure A. It's not the same for all structures. For each structure, it's an ordinal alpha, such that if 2 tuples are alpha related, then they are automorphic. So one thing I guess you can try as an exercise if you want to see how this works is that the opposite is always the case. So for all alpha, so if A is automorphic to B, then A is less than or equal to alpha than B. That's always the case. And if you're gonna play around with the definition a little bit, that's an exercise you could do. But the other way around is not the case until you reach this ordinal. So Scott's theorem says that there's always an ordinal alpha that is countable, that is large enough so that you get equivalence. Actually, so then that means that here you get equivalence. Because this arrow is always true for free. The interesting one, the new one you get is the one going there. Okay, so we'll prove this in a couple of lectures. So that's what Ash and Knight used to define their Scott rank, which is not the one I want, but it's close. Is the least alpha for which this happens. I guess Scott theorem is not for countable structures. Scott theorem is in general. This is always true for uncountable structures too, and you get an uncountable ordinal. If the structure is countable, then the ordinal that you get is countable. And for this course, we only care about the countable structures, so it's all countable ordinals. Okay, so this first structure, such as for every A and B in A, this happens. And this is the idea that I was telling you before about how to define the Ash-Knight rank. The first point when the back and forth relation coincide with automorphism. Cool. So far, so good. Okay. Do not read. It says here. So do not read. Because it's just messy. But what I want to say with that part is that what I call the back and forth rank is not exactly the same as this. It's slightly different. It's just a technicality. It's still a notion that is defined in terms of this back and forth relation and that implying isomorphism, but it has a few quantifiers. And the reason I like this definition is because this is the one that is robust in terms of all the other ones. Let's not worry about it. so far. Let me just tell you that this new this back and forth relation is very close to the Asian Knights. It's not close to Scott's original. It's quite far, omega times omega factor. But it's close to the Asian Knights by a factor of 1. Depending on the structure A, you might get equivalence here, or you might get equivalence here. That depends on the structure A, but it's always either equal to the Asian Knight rank or the Asian Knight rank plus 1. It's equal to one of those two. But then this one is the one that is robust, as we're going to see in what's coming. Cool. Okay, so that's about the back and forth relations that we're going to go deeper and calculate some ranks and prove this theorem of Scott in a couple lectures. Any questions? This is a good moment to ask questions about that. There is something in the chat. Oh, is alpha always countable? Yes, I didn't mention, but yes, alpha everywhere I mention it is always countable. We'll only deal with countable ordinals. Though everything on this slide actually is true for uncountable also. So I'm not thinking of the uncountable case. I'm keeping the countable case in mind, and I might forget to say countable. So it's a good question. But actually, these definitions and this theorem, they all work for the uncountable case too. So that's true too. Any other questions? You can ask in the chat if you want, or just by speaking. Is less, that's a good question. Yes, so that is the case. Yes, so these relations, as we're gonna look at all the details, so we're saying later, but yeah, it's true that if you have the beta is less than alpha, then if a tuple is alpha related, sorry, then oh, that was a bad arrow. Then the tuple is beta related. So yes, the relations, they are getting finer and finer as you go up in the audience. So they are coarse at the beginning and they're getting finer and finer and finer. And as I was saying, the exercise, A automorphic to B implies this one. So they get finer and finer and finer and finer until you reach automorphism. That's the picture you have in mind. And actually, you get more. If alpha is actually less than beta, you also get a greater than or equal beta. That's hard to see. So actually, you get equivalence. If you're just less than or equal at one level, then at all the previous level, you are equivalent. So you get more than that. Any other questions? Cool. Okay. So we'll we'll go deeper into this in a couple of lectures and go look at these properties and everything. But we'll continue with the overview today. Okay, so the second technique for measuring complexity is looking at these notions from descriptive set theory, the Borel and Bayer complexity hierarchies. We're going to use it for two types of aspects of complexity: identification, which means identifying the structure within the others in a pool of structures, and isomorphism complexity, which means finding isomorphisms between the structures that you know are isomorphic, but you don't know how to find the isomorphisms. We might get into this on Friday or maybe something else. There are many more things that we could do, actually, but that's a possibility. Okay, so let's get into this. Okay, so and this is the kind of the beginning of computable structure theory, is this observation that if you have a countable structure, it's isomorphic to one whose domain is the natural numbers. Now let's assume for this, let's imagine it's an infinite countable structure. So if it's infinite countable, the domain is isomorphic to, it's in bijection. You can find a bijection with the natural numbers, and through the bijection, you can carry through all the operations, and you have another structure whose domain is the natural numbers. The relation operations on these structures might have nothing to do with the relations and operations on the natural numbers. But as domain, you're using the numbers, the standard numbers, which means, first, it means you can do computability, because now your relations and functions are functions and relations on the natural numbers. So you can use techniques from computability. And also you can use, in this case, techniques from descriptive set theory, which is the ones that we're going to care about today. Okay, so fix a vocabulary tau. So by a vocabulary, I mean a set of constant symbols, relation symbols, and function symbols. Okay, out of which you define a first order language, essentially, or the structures. Okay, so the vocabulary, if you want, in your head, just think of the vocabulary of order groups. You have a constant E, an operation star, and an ordering less than. If you want just to fix ideas in your head, but this could be any vocabulary, any countable vocabulary, this is going to work. I'm going to use that for the example, that particular case. Okay, so I'm going to use this notation. And again, there are a few notations in the literature. This is one. Chi sub tau is a set of all structures on this vocabulary tau with domain the natural numbers. Okay, so all tau structures whose domain is the natural numbers. As we noted above, if you have a countable structure, any countable structure is going to be isomorphic to one that belongs to chi tau, to one whose domain is the natural numbers. So by doing this, we are not missing any countable structures. They are all represented there. But now we have a space where they are all represented there in a nice, well, I don't know if nice way, but in some way. Okay, so okay, this is, I'm just repeating this, essentially the same definition, just to make sure everybody got it. So a structure C belongs to this space chi tau if and only if it's of this form, where the domain is the natural numbers, and then these constant function and relations are anything on the natural numbers. Right, so here's where, right, so where E is a constant in natural numbers, star sub C is a function from the pairs of natural numbers to the natural numbers, any function. And less than or equal to is a binary relation on the natural numbers, on the pairs of natural numbers. Sorry. Right? Okay, so that's what chi tau is. So that means that to represent this structure C, well, the domain is always fixed, right? But then this constant could be any number. This operation could be any function from n squared to n, and less than or equal could be any relation from n squared to 0 to 2. So the set of all structures in chi tau is essentially the same as this product of natural numbers, functions from n squared to n, and functions from n squared to 2. Right? So here we get representations of all structures in chi tau. Okay, so that's, because here we have the E, and here we have the star, and here we have the S. Now, using some arithmetic of exponentiation, which actually works in this case, that's the same as that, if you guys believe it, which you can show this whole thing is isomorphic to set of functions from the natural numbers to the natural numbers, if you do it the right way, or as a subset, I guess, on the function from the natural numbers to the rational number, right? So encoding, if you encode these pairs of numbers by a single number and this other pair of numbers by another single number, and then these two, you allow it to be n, that's why we have a subset. We get this n times n here, this n times n comes here. And then this is just a countable set, so we can code it by the natural numbers. So using coding a few times the right way, you can view the space of tau structures as a subset of n to the n. It's a subset of Bayer space. Luigi, you said these people are more or less familiar with these kind of things?
Maybe not everyone know familiar with Bayer space.
Okay. So far I haven't said much about it. So only the notation. So this here is a set of functions from n cross n to n. That's for notation, and then so that's kind of what these guys are. These are functions from n cross n times n to n, right? That's what the operation is. And then just by doing some coding pairs of elements into elements a few times the right way, you can encode any structure as a subset of just single functions from n to n. But now, instead of the domain being, when you look at the elements of the domain and function, they could be representing either the operation or the relation, the tuples, or anything. So this is just doing some coding. And n to the n has a topology that comes associated to it, with it. Which is given, for the ones that I know, is given, let me see if I have to say something else, I don't see anything else. Is given by the power of the discrete topology on n. Okay, so there are various ways to define the topology on this set. It's called Bayer space. Out of which this is a subset, right? A subset. On Bayer space, there is a standard topology that people use, and it's given by the power of the discrete topology on n. So for the ones of you who learn some topology at some point, you probably know how to take the power topology, like when you have something like a set of functions, like in this case, on some space, you can assign topology to it. And if and other ways of defining this topology, let me just do it here. One is to say that if you have a finite string, you can define the set, this bracket, square bracket sigma is a set of all the functions f that belong to n to the less than n, which starts like sigma. So sigma is a finite string and it's telling you the beginning of the function, the first values of the function. So such that sigma is a subset of f. That's the way we say that. So we say sigma is a finite tuple, let's say of length 5. Essentially, it's telling you what the value of f0, f1, f2, f3, and f4 should be to belong to this set here. Okay, so this set is all the functions that are compatible with sigma, with the string sigma on the length of sigma. So this topology has so these are the basic open sets of the topology. The topology is defined by these basic open sets, meaning that every open set in topology is a union of these guys. So those are exactly the open sets in your topology, the unions of things of this form. And then on that topology, another way of defining topology will be to, if you have a sequence of functions, one is that a sequence of functions converges to another, and it does if it pointwise converges to that one. Like for every value that you want to calculate, you look at the sequence of functions, that value on the sequence of functions, and eventually stabilizes and it's equal to what you want at the limit. So it's kind of like the obvious limit, it's eventual stabilization for each point. So we can go into, if you go into these parts on Friday, we can go slower through this topology thing. Okay. Cool. Okay. So we have a space of structures on our tau, and it has certain topology. For a structure A, we're going to define the set of copies of A to be the set of copies of A, to be the set of all the other structures, tau structures, that are isomorphic to it. Okay, so these are structures with domain omega, but if you have countable structures, there are many bijections with its domain and omega, so there are many ways to represent this single structure as one with domain omega, because there are all these bijections with omega, and they're all isomorphic. So this set copies A is a set of all the other tau structures with domain omega that are isomorphic to A. Okay, and then we don't even need A to have domain omega there. Okay, a couple of questions up here.
I think we have questions in the chat box.
As extensions of quantifier free formulas and their name. Yes, that's exactly right. So the basic open sets in this space of structures are essentially what you get by taking a quantifier free formula and taking on all the structures that satisfy this quantifier free formula about certain elements. Let me see if there's an so if I have so for instance I have a formula that says so 0, let's say 0 is the element from the natural numbers, star 1 equals 0, and 0 less in this is in the structure A 2, this is a quantifier free formula, and not the constant E equal to 1. This is a quantifier free formula. Let's call it phi. Then we can consider the set phi is a set of all the structures that belong to chi tau such that A models phi. So the 0 here is the 0 of the natural number. These are the numbers in the these are the natural numbers elements that we are using as domain. So this is essentially almost like a basic open set, because when we do this equivalence from here to here, every number kind of corresponds to, it's not exactly the same, but more or less. Every number corresponds to quantifier free formula. So this will be a different way. It's not, it doesn't follow exactly from the way the way I did it, but it is true. So the question is a good one. Yeah, still basic open set. That's actually right. With that definition of basic open set, they could be considered basic open sets too. These ones, but this will be another way of defining the topology so the topology on chi tau has as basic open set. And if you want, if you want to use the other one, you can say sub-basic. This is fine. The set of the form phi for phi quantifier free and about the elements of the presentation of the natural numbers. So these are your basic open sets. So yes, Sulin, that's a good question, and that's another way to see it. And again, I'll make sure to go through these things if you go deeper into this. Cool, thanks for the question. Okay, so we have this topology on this chi tau, which is quite natural.
Is it the natural point break?
Say that again.
Do we need a break?
Yeah, we need a break. I think it will be a natural break in maybe 2 or 3 slides.
Yeah.
Yeah, I was counting on that. So let's continue another maybe 15 minutes and then we take a break. Okay, so copies of A is instead of all the copies of all these copies of A. So Lopez Escobar, and I guess Scott follows from both of them, this theorem, that for every countable structure, I guess here everything is countable in this talk, the set of copies of A is Borel. So when you have a topology, you can define the class of Borel sets. I don't know how familiar is everybody with this. So here's the definition. The Borel sets are the smallest sigma algebra containing the open sets. So sigma algebra is a collection of sets which is closed under complements, countable unions, and countable intersections. That's a sigma algebra. So I guess an algebra of sets is a collection of sets that is closed under the Boolean operations, meaning negation, intersection, and union. When you put the sigma up front, you mean that you're allowing countable unions and countable intersections. Okay, so sigma algebra means you're closed under complements, countable unions, and countable intersections. So the Borel sets are the smallest sigma algebra that contains the open sets. So the open sets are not necessarily a sigma algebra because they are not closed under complements. Like the complement of an open set is a closed set, and a closed set does not need to be open. So you need to add more things to them to get a sigma algebra. So if you add everything you need, so essentially you start with the open sets and start taking countable unions, countable intersections, and complements, whichever way you want. And you do it until you end up with a sigma algebra. Those are your Borel sets. So your Borel sets are built from the bottom up, from the open sets, doing countable intersections, countable unions, and complements. And actually, you don't need to use complements to get Borel, because the complements, you can bring them all the way to the inside by using the De Morgan laws. So maybe you can apply the complementations at the beginning if you have any set that is defined in terms of complements. And then in the case of this topology, in Baire space, the complement, well, the open sets are already unions of Kloppen sets, and the complements of open sets are therefore intersections of Kloppen sets, of this basic the elements from the basis of the topology. So with the closed sets, you can build as intersections of basic open sets in this case. So you don't need the complements. You can just take unions and intersections and you get all the Borel sets. So you start only from this Kloppen basis that we have. Kloppen means open and closed, and all the ones in the basis in Baire space, they are open and closed. And you just close under countable intersections and countable unions, and you will get all the Borel sets. Okay, so this is a very large CMAL algebra. So it's a very large collection of sets, the Borel sets. But then they are not all the sets. They can be defined from the bottom up. They have some nice properties. They are somewhat constructible because you can build them from the bottom up, applying countable unions and countable intersections, these Borel sets. So in descriptive set theory, when in computability for us, in computability, a simple set is something that is computable. That means easy. In descriptive set theory, sometimes a Borel set is something that is easy. Constructible means Borel. So Borel means simple in some sense, which is for computability, this is not simple at all, as we'll see. So Lopez Escobar is quite interesting in that sense. That is saying that the set of copies, the complexity of the set of copies is not that bad. It's Borel. And we're going to use this to define a notion of rank. In terms of the Borel complexity of the set of copies. That's what you're going to use that to define a rank for the structure A. Okay, so let's look at this first, how to measure the Borel complexity of a set to begin with. So what we're going to do is we count alternations of countable unions versus countable intersections. So here's a definition. We say that a subset, and this is actually true for any other topological space. It doesn't need to be just a space of structures or Baire space. We're going to use this notation. So sigma n, we're going to say that a subset of chi tau is sigma n if it can be defined in that form right there. So it's a countable union of countable intersections, countable unions, countable intersections, and you have n alternations of that, of a collection of Kloppen sets that are indexed by this A0, A1, A2, A3. Those are the indices of these Kloppen sets. So you start from these Kloppen sets, the union intersections, union intersections. If all you need to define your set is n alternations, and you start with a union, you say that your set is sigma n. Okay, and you say that a set is pi n. It's essentially the same definition, but now here you're starting with an intersection, and there you're starting with a union. So, and the Kloppens, the complement of a Kloppen is Kloppen. So you can see how the sigma n sets are the complements of the pi n sets by the De Morgan laws. The unions become intersections. Okay, so those are the pi n subsets, and then this is. You see that this is kind of bold. These are usually called boldface pi n and boldface sigma n. Is boldface fonts being used there. So for instance, sigma 1 set is the same as open, right? Because an open set is a countable union of Kloppen sets in this topology. And that's what sigma 1 means. Just one union, and there's no alternation, so it's just one union of Kloppen sets. So sigma 1 is a synonymous for open sets. And therefore pi 1 is synonymous of closed sets. And then there is, I don't know if you have seen this before, but there is sometimes people talk about these sets that are F sigma. and they are exactly the same as the F sigma 2 set. So F sigma means union of closed sets. So, and then and G delta means intersection of open sets. I don't know if you have seen that. Essentially, you have to read this F means closed, and in some language is open. The sigma means union, and the delta means intersection. I don't know what language. Fermé, close, I guess. Open with G. I don't know what language, but that would be German or French. Well, okay. So those are familiar classes that people use, but then this hierarchy goes on and on, counting alternations of modifiers. The union, like what if you take all these classes of sets and the unions, so all the sets that you can define with any number of alternation modifiers, like any finite number you want of alternation modifiers, what we get by unioning all these classes of sets is not yet a sigma algebra. Because it's not closed under countable unions, because you might take one set that is by 1 and one set that is sigma by 2 and one set that is by 3 and one set that is by 4 and so on, and the union of all these sets might not belong to any of these guys. It's going to belong to a later level, right? So it might not be closed under countable unions because you can take elements from different levels. So you need to use ordinals to actually, you need to go through the ordinals, keep on iterating these to the ordinals to get a sigma algebra. So the definition is like this, the general definition. When you have an ordinal, you say that a set is sigma alpha if it's a countable union of pi beta sets for beta less than alpha. So it's a recursive definition. We are using, and a set is pi alpha if it's a countable intersections of sigma alpha, sigma beta sets. So it's a recursive definition of what it means to be pi alpha and sigma alpha. We assume we already know what it means to be pi beta and sigma beta for beta less than alpha. So we assume you defined those before, and now we use the previous sigma beta collections to define what it means to be pi alpha. It's a countable intersection of sigma betas for beta less than alpha. And the elements, this countable intersection, they may have sets that are sigma betas for different betas less than alpha. Okay. And then these are enough. If you go through the countable ordinals, then you get all the Borel sets. So actually, yeah, so every Borel set you can prove is pi beta for some countable ordinal beta. And yeah, so omega 1 is the first point when you actually get a closure and you get a sigma. So every Borel set is pi alpha for some alpha. I'm just recalling the definition of what it means to be, what are the copies of A. And I'm reminding you what I mentioned before, that the set of copies of a structure is Borel. So now with that in mind, we can define the Borel rank of a structure A to be the least alpha, such that the set of copies of A is pi alpha plus 1. And the plus 1 there comes to make it match with the other definitions. So I guess you could have defined it to be without the 1, essentially. The 1 there is the one that gives you the right definition. Okay, so we know the set of, for every structure, the set of copies of A is Borel. If something is Borel, then it's pi alpha for some alpha. So look at the least alpha. So that is pi alpha plus 1, essentially. And that's going to be our rank. So different structures, for different structures, the set of copies is going to be more or less complicated. And so how, depending on how complicated it is in this Borel hierarchy, that's going to be our Borel rank. And one can show that this Borel rank is exactly the same as this back and forth rank that we defined using the back and forth relations a few slides before. Right. So these examples, we can look at this also later when we can consider this in more depth. So the set of copies of the ordering of the rationals is pi2. So this, remember, this is G delta in the space of structures. So that gives the rationals rank 1. We said before they had rank 0, but that was the Ashen Knight rank, the one that wasn't exactly always right, it was plus or minus 1. So the rationals, according to this definition, have rank 1. And the integers, this takes a bit more work to see, but the set of copies of the integers is pi3 in the hierarchy, and that's going to give it rank 2, which is what we got before. Yeah, so we can go into the examples of some of these things later on. Okay, so right, so you can see here. So it's a way of defining rank, just looking at the Borel at the level in the Borel hierarchy that we get the set of all copies. The definition is very different than the back and forth definition of rank using the tuples and comparing these back and forth relations between the tuples to figure out at one point we get that the back and forth is the same isomorphism. So they are very different definition of ranks. They turn out to be exactly equivalent. Okay, so these two definitions of ranks give you exactly the same rank. The back and forth relations have, well, once they are closer to the original definition of Scott, that's why I gave them first. But another reason why they are good is because they help with when you actually want to calculate the rank, they give you the combinatorial tools to do it, as we're gonna see. I think we're gonna see it later. So in terms of combinatorial tools, the back and forth relations are a bit better. Though this notion of Borel rank is kind of, I guess it couldn't get more natural than that in a sense. Okay, I think this is, before we get into isomorphism functions, it's a good place to take a break.
Yes. Shall we break until 9:45 or have a longer break?
Half an hour, is it?
Do we need a longer break, a half an hour break, or we just resume at 45?
As you guys wish. Probably people want to rest a bit.
Okay, so if you don't want to stay too late, then we just resume at 45.
Okay.
Okay, see you.
All right, so welcome back, everybody. Should we make sure everybody's back from their little breaks? I guess we can see. Okay, the slides are there. It's a good moment for questions too. If anybody has questions, no way. No questions. Okay, so that was the Borel complexity, and this is a, oh, by the way, this is a method this is a record identification complexity, right? So you are identifying like copies of A, right? So what is pi alpha plus 1 here is to identify that something belongs to the space, the set of copies of A. So this is identification complexity, being able to identify the structures that are isomorphic to A from other structures. So that's identification complexity. And now we're going to go to isomorphism complexity, which is finding isomorphisms between representations of the same structure. Okay, so here is the way we formalize this isomorphism complexity. So we say that a function f like this is an isomorphism function for A if it's a function of the following kind. So it takes as input two copies of A, so two structures that belong to chi tau, so the space of structures, and which happen to be isomorphic to A. And as output, it takes a map from the natural numbers to the natural numbers. Recall that the domain of these structures are, for both, are the natural numbers. The domain of both of them are the natural numbers. So the output of this F, when you apply it to these two structures C and D, it should be an isomorphism from C to D. Okay? So that's what we call an isomorphism function for A. The function is given two copies of A, and it outputs an isomorphism between them, or from the first one to the second one. Okay, so that's an isomorphism function for A. And the idea is to measure the isomorphism complexity of A in terms of the complexities of these functions up here, of these isomorphism functions. And how is that we're going to measure the complexity of these functions? We use the Baire hierarchy. The Baire hierarchy goes as follows. So a function is said to have Baire class 0 if it's continuous. Okay, so Baire class 0 is the same as continuous. Those are the simplest functions in this hierarchy. And then Baire class 1 is a function that is a pointwise limit of continuous functions. Okay, so of a countable, of a sequence of continuous functions. If you remember your topology, so you have a sequence of continuous functions, but the limit might not be continuous, right? You can have like the function, let's say, I mean, this space is Baire space, but just to give an example, let's say in 0, 1, if you have the function that maps x to the n, to the power of n, right? So you start with x to the 1 and x squared and x cubed and x to the 4th. They go like this, and they are going to converge to a function that is 0 up to 1, and then 1 gives you 1. So the limit, the pointwise limit of these functions exists, but it's not continuous itself. So this function that takes the values 0 up to 1 and then 1 is Baire class 1. It's a limit of continuous functions. By itself, it's not necessarily continuous. Okay. In Baire space, in the space of structures, there's much more. It's much more you can do with Baire class 1. But okay, that's the idea. Good. I think we should get into more details later, probably, because this is a bit technical to see these. Essentially, what's happening here, let me just tell you what's happening for like a general overview. So what I'm saying here is that if you have copies of the rationals, you can build a continuous isomorphism function. So what you're given here is the input is the structure C and the structure D, which they both look like the rationals. But then the first element, the elements are given that. So the seed of the natural numbers might be here, and here might be here. They have different representations. And the 1 is here, and maybe the 1 of the natural numbers is here, and then the 2, and then this 3. And you're given these, and you're supposed to build an isomorphism between these two structures. So you have to tell where 0 goes, where 1 goes, in a continuous way. If you look at this topology, which I don't want to get into details right now, but essentially continue means that if you start, you have to define the values of the functions as they come along, kind of So to define where 0 goes, you cannot look at the whole structure C and D, only finitely matched. So you can start by saying, okay, map 0 to 0, that's always fine. And then when you want to figure out where to map 1, you want to say, well, I don't want to map it to 1 because 1 is, it will be crossing. That's not good. So I have to wait until a little bit more. If I see a bit more of the structure D, maybe 2 is here, that's not good, but then I see 3 up here and say, okay, I map it there. Where do I map 2? Well, I can map it to 1 because 1 is on top. And if I keep on preserving the order, I can figure out how to do an isomorphism. And the fact that I'm only doing it finitely match the structures to figure out where to map them, that's gonna make these functions continuous. I don't want to get too much into details. For now, we can look at this more carefully later on. But in this case, we have a continuous isomorphism function. In the case of the integers, to get an isomorphism function, you need a function of Bayer class 1. And it's a bit more complicated. Essentially, if you start doing the same thing you were doing here, just keeping the order correctly is not good enough because maybe there are more elements in between these guys that there are elements in between these guys, and then you need to change the item there, where you map 0 and where you map 1. But you could do it in a way that whenever you see more elements in one side and the other side, you just keep on changing your maps, and eventually they're going to stabilize. And this idea that is eventually going to stabilize is what's going to give you a limit of continuous functions. You're going to be able to define the isomorphism as a limit of continuous functions because you're changing your mind, but eventually you're stabilizing, and that's what a limit of continuous functions is. Okay, this is just a general idea so you get a picture. But right, but in the case of Q, there's a simpler structure. You get a continuous isomorphism function. In the case of Z, that is a bit more complicated. You need to do Bayer class 1. It's a bit more complicated. Continuous is not enough. So that's the definition again of what an isomorphism function is. Let's just find the Bayer class more in general. Bayer class 1, we say, is a pointwise limit of continuous functions. Bayer class 2 is a pointwise limit of functions of Bayer class 1. Right, so this one is each one is a pointwise limit of functions in the previous class. So in general, we can define it like this. So function is Bayer class alpha if it's a pointwise limit of functions that are Bayer class beta for some beta less than alpha. Okay, and we have a hierarchy of functions through the ordinals. Okay, so the larger the alpha, the more functions we have in our class. And we can use this to define our rank using isomorphism complexity. So we say that given a structure A, we define its Bayer rank to be the least alpha, such that A has some isomorphism function that is Bayer class alpha minus 1. In principle, there is no reason to see why there is such an alpha, but I think we're going to be able to prove that. The other direction is hard, but at least down that direction of why there must exist such an alpha, that we might be able to do. But yeah, there is always such an alpha. Every Borel function is Bayer class alpha for some alpha. And there is always a Borel function. There is an isomorphism function on the structure. So it's going to be Bayer class alpha for some alpha, and we'll define the Bayer rank to be the least alpha with using alpha minus 1 under. And with that definition, one can show that the Borel rank is equal to the Bayer rank. I think that's quite interesting. Because the definitions are quite interesting, are quite different. No? So this is identification complexity. So you're saying how difficult it is to recognize the structure from the other ones. This is isomorphism complexity. It's telling you, you're seeing how difficult it is to find isomorphism between copies of the structure A. So in first sight, they are quite different things. But they turn out to be exactly the same, have exactly the same value. So that tells you that this Frank is onto something. It's telling you something interesting. Are we able to prove that fully? Probably not fully, but we can prove parts of that equality later this week. Any questions?
So is there a issue of hierarchy for bare class 1 functions?
I guess so. Yeah. They don't show up in here, but yeah, yes, there is. I mean, because bare class alpha is the same as pretty much. Yeah, it's a sigma alpha function. It's a function. Yeah, a function that uses Oracle 0 to the alpha, or x. The input is x. Use Oracle x to the alpha to give you the answer. Essentially, the alpha chunk. So yes, there must be some kind of hierarchy going on in the middle.
Okay, thanks.
Okay, any other questions before we move to the third technique? Cool. Let's move on. Okay, so the third technique to measure complexity is infinitary formulas. And actually, I'm giving this last, but actually this is the one I want to spend the most time tomorrow and Thursday. I think it's quite interesting, and then many ideas fit together, and it's probably easier to explain the results. And it's infinitary formulas, and we're going to use them to measure complexity in two ways: orbit complexity and identification complexity. So again, in the next few slides today, I give you more or less the general definitions, and I'll repeat these definitions tomorrow and go deeper into more examples, and we'll play more with it, and we'll prove some of the theorems that I mentioned here tomorrow. Okay, so the infinitary first order language. Let's define this, and again, I'll define it again tomorrow. So we start with a vocabulary, and by that I just mean, as I said before, a set of symbols that represent constants, functions, and relations. That's our vocabulary. Some people call this a language, but since there is a first order language, the infinitary language, I'm dealing with different languages, I prefer to use vocabulary for the set of symbols. For instance, if you want to fix one vocabulary in your head, you can use that one of arithmetic, or the groups, or whichever you want. You'll fix one just to keep in your head. So that's the vocabulary we fix, and then we then have rules that using the vocabulary we can define. Well, I guess first order logic. I assume people know how to define the formulas of first order logic using a vocabulary. Luigi, this is correct? Yes. So okay. I assume you all guys know what first order logic is, and what are free variables. And for everything to make sense, given a formula, given a structure, formula, and a tuple, we need to be able to define what it means for the formula phi to be true about tuple A in the structure, which you define by recursion if you want, and I assume you all guys know how to do this. And by the way, this is phi true in A about tuple A inside A. That's we write this way. Formula phi is true about tuple A inside the structure. Okay, in a first order language, what it means to say first order is that the quantifiers for all and exist range over elements of the structure and never range over subsets of anything else. If it was subsets, if you could use subsets of the structure, then we have second order logics are not good. So first order means quantification ranges over the elements of the structure. And the word infinitary up here refers to the fact that we're going to allow our conjunctions. A conjunction means ands, and disjunction, this means ors, and our disjunctions, so our ands and our ors, to be infinitary. So meaning we can take an and of an infinite number of formulas. We can take an or of an infinite numbers of formulas. So conjunction means and, disjunction means or, and they could be infinitary. So it's still first order. This is infinitary first order. It's still first order because for all and exist still range over elements of the structure, but it's not elementary anymore. It's now conjunctions and disjunctions are allowed to be infinite in this infinitary language. Okay, so I'm just repeating what I just said. So we have in the slide, and here is an example. Suppose we have a group with identity E and an operation asterisk or star. So how do you say that an element is torsion? Let's think about it. So torsion, an element being torsion in a group means that if you raise it to some power, you eventually get to the identity. Okay, there is some power that you can raise the element to so that you get the identity. That's what it means to be torsion, right? So you're not torsion if you all your powers are all different and you generate a copy of Z, let's say. But torsion means you generate the group generated by the element is a finite group. How do we say that? There's something we cannot say in first order logic because we don't know how long this power is gonna be. Right? In here we only have multiplication, so we don't have power to the n. We can just write power n times. So the way you write this in infinitary first order logic, you do this is an infinitary disjunction. Sometimes I write this as a double or just to emphasize that it's an infinitary disjunction. It's an or of infinitely many formulas, one for each natural number n, and the nth formula is the one that says that x to the power of n plus 1 is the identity. Okay, so this is saying for some natural number n, the n plus 1 power of x equals the identity. So that's the same way, the same thing as saying that the group is that the element x is torsion in the group. Okay, so we couldn't say this in first order logic because the larger the n, the longer this is. Right? In first order logic, we can only formula first order logic is going to be a finite set of characters. We can only talk about powers up to a certain number in a fixed formula. In a single formula, we cannot talk about powers of arbitrary size, only up to a certain formula. And this case, torsion is something that we cannot define. I'm guessing it's a standard exercise, I guess, when you learn, I guess, basic logic and compactness to show that this notion of torsion, this relation of torsion, is not first order definable, like elementary first order definable. So I don't know if you've seen that when you learn your compactness, but yeah, this is the notion. This relation of torsion, it cannot be defined by a first order, a finitary first order formula. You need infinitary logic to define it. Divisible, an element of the group is divisible if this is what that means. If for every natural number you want, p, there is a y such that y to the p equals x. That's what's written over there. So conjunction over n for over all n. So there, for every n, there exists a number so y to the power of n is x. So it's the name divisible comes when you think of additive groups. This y is essentially like x divided by n. When you look at multiplicative groups, this y is the nth root of x. So divisible in this case means that every x has an nth root for all n's. But again, this is something that you couldn't define in finitary logic. You need this infinitary conjunction over the natural numbers. So you can think of this infinitary conjunction of the natural numbers as saying like for every n in the natural numbers, but recall that's not a first order thing, because in first order the quantifiers are only allowed to range over elements of your structures, that meaning elements of your group, right? So you're not allowed to quantify over natural numbers in first order logic, only elements of your structure, in this case the group, right? So so this infinitary conjunction disjunctions allow you in a way to quantify over natural numbers. That's what essentially what you're doing in your formula. So this conjunction up there is like quantifying over natural numbers, and then this one up here is like quantifier over the natural numbers too, which is not something we have in a finitary first order logic. Okay, so that's what infinitary logic is. It allow us to do this infinite conjunctions and disjunctions. And it's pretty powerful. So Scott in 65 showed that every if you have a subset, if you have a structure A, so this is for given a structure A, every subset of A to the K, so every set of K tuples that is automorphism invariant, meaning that for every automorphism of A, the set B stays the same. So you can move the elements of A around using an automorphism, but this relation B, the elements of it stay the same. There is an infinitary formula with a variable x, such that B can be defined by that formula. So that this set B that is invariant is going to be the set of all tuples B that satisfy this formula. Okay, so one thing to notice, if a set is defined this way, it needs to be invariant under automorphism, right? Because if one tuple satisfies a formula, any other tuple that is automorphic to it must also satisfy the same formula, right? So if you're automorphic, you satisfy all the same formulas. So any set defined like this using a formula needs to be invariant under automorphisms. I'm guessing also when you learn first order logic, one of the things you learn usually is that one way of showing something is not definable is by showing that it's not closed under isomorphisms, under automorphisms. But in this case, we have the reverse. So Scott's term says that if a set is automorphism invariant, then it must be definable by an infinitary formula. So this is not true in first order logic. Again, you can do compactness to show like essentially like these guys are not definable in first order logic, but in infinitary logic, everything that is automorphism invariant is definable by some formula. So the orbits of the tuples are automorphism invariant, right? The set of everything that is automorphic to a tuple is invariant under automorphism pretty much by definition. So we can measure the orbit complexity of structure A using the complexity of these formulas that we need to define the orbits. So we'll prove this tomorrow. Another theorem of Scott I will also prove tomorrow is that for every countable structure A, there is an infinitary sentence or sentence in the infinitary language. It's called size of A, that depends on A, which satisfies the following property. So a structure C satisfies it if and only if it's isomorphic. Of course, if A satisfies psi A and you're isomorphic to it, then you must satisfy it, right? So two things are isomorphic, they satisfy the same sentences. So this sentence has the property that is true of A and is not true of anybody that is not isomorphic to A. So it identifies A uniquely. So it's only true of A and things that are isomorphic to it, and it's false about things that are not isomorphic to it. So it's a sentence that gives you identifies A completely. And so this formula is something that we can use for identification complexity, because this formula is identifying A from the other structures that are not isomorphic to it. So, okay, so then we can use these formulas to define the orbits and these formulas to separate the structures from the others. So now the idea is to use the complexity of these formulas to define a rank. So now we need to define what is the rank of these formulas. Okay, so now we need to look at the complexity of infinitary language. And like before that we did, we counted alternations of unions and intersections with Borel. So now we are gonna do alternations of exists and ors on the one hand, and for alls and ands on the other hand. And then these ands and ors could be infinitary. And remember that these infinitary these are almost not the same, but essentially what's going on is that you're doing quantification over the natural number. So it is alternations of exist versus alternations of for all, in a sense. So here's how we do it. So a sigma n formula, infinitary sigma n formula is one of the following form, and the form has, okay, so something that is quantifier free deep inside, so many things are quantifier free, and then it starts by a disjunction of existential, of conjunction, of for all, of disjunction of the exist. And then we'll count the alternations, but we are pairing up exist and this and ors, we put them together, conjunctions and for all we put them together, disjunction and exist together, these go together, and then we count the number of alternations of those. Okay, so putting these guys together. So make sense? So in a sigma n formula, we have n alternations, and we start with disjunction and there exists. That's how we define the sigma n formulas. And deep inside we have quantifier free. And a pi n formula is essentially the same thing, but now we start with a conjunction and for alls instead of disjunction and there exists, and then we are flipping everybody. Okay. So that's how we count alternation of quantifiers. Again, not every infinitary formula can be put in this form of either one of these two forms. So it's the problem. So not every formula can be put in this form because we need to go to the transfinite levels to reach every infinitary formula. So just going through the finite level sigma n and pi n for finite n is not enough to consider all the infinitary formulas. We need to go into ordinal depth. And then this is a similar idea like in the Borel complexity. So you say the infinitary formula is sigma alpha if it's of this form. It's a disjunction of existentials of formulas which are pi beta for beta less than alpha. And you say that a formula is pi beta if it's a conjunction of folds of formulas that are sigma gamma for gamma less than beta. All right, so again, we define the sigma beta and pi beta by recursion from using the previous one. Okay, so sigma alpha is disjunction of pi beta for most smaller beta, and pi beta is conjunction of folds of sigma gamma for smaller gamma. So I'm repeating the theorem again, the one we mentioned before. So Scott proved that if a set B is invariant under automorphisms, then it's definable by some infinitary formula phi. So we can define the orbit rank of A to be the least alpha, such that every automorphism orbit is sigma alpha definable. And the fact that there exists such an alpha, that it means a proof, such that all orbits are sigma alpha. But well, I mean, I guess it's not much of a proof, right? So once you know that every infinitary formula is sigma alpha for some alpha, and there are only countably many tuples, so there are countably many automorphism orbits, there is going to be at least alpha such that they are all sigma alpha. So I guess that's why you need to know that. So the orbit rank is measuring the complexity of the automorphism orbits. So it's the least alpha such that all of them are sigma alpha defined. So let's just erase the theorem. The other theorem of Scott's that we mentioned before is that for every structure A, there is this sentence psi that we call, it's called the Scott sentence of A, that satisfies that it's true of a structure if and only if the structure is isomorphic to A. So it's true of A and it's not true of anybody else. And the Scott sentence rank of A is the least alpha such that A has a pi alpha plus 1 Scott sentence. So there is a pi alpha plus 1 sentence true only about A among countable structures. So yeah, when I say that this sentence is true about A and nobody else, I'm only restricting myself to countable structures. Okay, so it's kind of the simplest complexity of such a formula you can find. So this one, this formula is identifying A from the other structure. So that's why this is identification complexity. And this one is measuring the complexity of the orbits. So that's why it's orbit complexity. I erase that again. And okay, so this Scott sentence rank is equivalent to the Borel rank. And that follows from, I guess, the results of Lopez Escobar, but then there was an improvement of the result by Vought in 75, and that's what you need to use here. But those two ranks, the one about Borel complexity in the Borel hierarchy, and this is Scott sentence complexity, are the same. This follows from the result. Both of these notions are identification complexity. So this is identifying the structures in terms of a sentence that is true about it and about nobody else, and this identifying the representations of the structure, the copies of the structure. So they're both identification complexity, but one is, but using different techniques, they turn out to be the same. And this Scott rank, it turns out, is the same as the orbit. So these two are the same. And they are measuring different things. Now notice that again, there is alpha plus 1 hanging in here. That is put there so that we get equivalence. Otherwise, we will get equivalence plus 1. But even with all notions of Scott rank, the ones I mentioned, Scott, Session Knight, all the original ones before, you didn't even get this plus 1 equivalence, because for some structures you get plus 1, for some structures minus 1, for some structures plus omega. So the fact that we are just manipulating this a little bit doesn't mean much. So you couldn't do that before for the other notion. So this has the right definitions, so that they are the same. The fact that we are choosing the sigma and the pi here, that's important to make everything work out fine. So you could choose the pi here and the sigma, but then then you don't get a robust notion if you don't use the sigma here or you don't use the pi here, for instance. But again, we'll see that tomorrow. So let me mention a few examples that we mentioned before. So we said in the case of the rationals that two tuples are automorphic if the ordering among the elements is the same on the tuple. And that's something we can say with a quantifier-free formula, right? So if you take this tuple in the rationals, it has 3 elements, 1/2, 7, and 4. The automorphism orbit of this tuple is defined by defining the ordering of the elements. And that's x1 is below x3 and x3 is below x2. That's all you need to know. So whenever you have a tuple x1, x2, x3 that satisfies this, it's going to be automorphic to that one in the rationals. And this formula that is defining the orbit is quantifier free. So in particular is sigma 1. This is sigma 1. So this means that the orbit complexity of the rationals is 1. So all the tuples have a sigma 1 definitions. What about the Scott sentence? A sentence that is only true about the rational numbers and is not true about anybody else. So the ordering of the rational numbers is the unique countable linear ordering that is dense structure that is a dense linear ordering with no endpoints. Probably some of you know this. So there is a unique linear ordering that is dense, meaning that between any two elements there is an element in between and has no endpoints. They are all isomorphic to each other, and they are isomorphic to the rationals. And then this you can write with an infinitary formula. You have to say that it's a linear ordering, so that's the 3 axioms of linear orderings. You have to say dense for any 2 points there is one in between, and you have to say no endpoint for every point there is one below and one above. And that's, if you write that down, if you go and do the exercise writing it down, you will get an infinitary pi 2 sentence that identifies the rationals. And that gives you that the rank is 1. Remember that in the definition up here of the ranks, we use alpha plus 1 in this case and alpha in this case. So that's one here, we get the 2 and the 1, alpha plus 1 and alpha. So alpha is 1, that's the alpha. In the case of the integers, if you want to define automorphism orbit of, let's say, this guy up here, -1, 2. To be automorphic to that one, what you need to say is that, well, you need x1 to be below x2, strictly below, and you need to have exactly 2 elements in between, right? Any other tuple such that the first element between the number of elements between them is exactly 2 is going to be automorphic to this one, right? You can just, the automorphism of the integers are just the translations. 2 tuples are going to be automorphic if you translate one to the other. So that means the number of elements in between has to be the same. And you can write that with that sentence. There exist 2 elements that are in between x1 and x2, such that any other element between x1 and x2 is equal to one of them. That's what that says. There exists exactly 2 elements between x1 and x2. So that defines the orbit of the pair -1, 2. And that formula there is sigma 2. So exist, and then for all up here. That makes it sigma 2. If you count the quantifiers. if you want to define a sentence that is true about the integers and is not true about anybody else, you have to say that it's a linear ordering, that it has no endpoints, and that all intervals are finite. If you say that, then you will uniquely identify the integers with the orderings. And did I write that down? No, I didn't write it down, but that one is pi 3. Because saying like all intervals are finite, that's pi 3 part for every 2 elements that exist, and things, some number of things in between and nothing else. That is 3 quantifiers, pi 3. And then you get that the rank of the integers is 2. And then again, you get the alpha and the alpha plus 1 right there. Okay, so the integers are a bit more difficult than the rationals. Okay, so they're putting everything together that we've seen so far. We see that we get this theorem. This is a theorem that we get together, putting everything we did in the talk today. So given us a structure A and an ordinal alpha, the following 5 things are equivalent. There are 5 statements up here. All of them are equivalent. This one is the one that I mentioned that I said do not read. This is the back and forth complexity that essentially is the least alpha, such that when you're equivalent, when you're related to alpha, then you're automorphic, but it's a bit more than that. Don't worry too much about it. That's one way of measuring the complexity of orbits. The other way of measuring the complexity of orbits was saying that all automorphism orbits in A are sigma alpha definable. So the notion on top, based on this back and forth relation, is equivalent to this one about being sigma alpha definable. We're going to show that using infinitary formulas. Those 2 things are equivalent to saying that the set of copies of A is pi alpha plus 1 in the Borel hierarchy. It's the simplest way of finding this Borel set. And that's the same thing as saying that there is a Scott sentence, so that is pi alpha plus 1. So there is a pi alpha plus 1 sentence in the infinitary language that uniquely identifies A up to isomorphism. And that is the same thing as saying that the structure A has an isomorphism function that is bare class alpha minus 1. And that's, yeah, a completely different way of saying. So this theorem essentially says that the rank, well, we can define the rank of A to be the least one, such that the least alpha that makes all of these true, given the structure A. And we are going to get this, the back and forth rank, the orbit rank, all the ranks that we mentioned, all of them are the same. This is the Ordinals. No. So that's why I call this one like the robust definition of Scott rank, because we get the equivalence between all these different ways of comparing, of measuring complexity. They have to be defined the right way to do the equivalence, right? So they were definitions that were similar with similar ideas, like using different back and forth relations, or not these, or not the sigma alpha, or not, well, this was not. This is the way, if you define them this way exactly, you get the equivalence. So that's, for me, tells you that this is in a way like the right definition of Scott rank. So the goal for the following days is to go deeper into some of these notions, mostly to teach the students, about infinitary logic, not only to prove the theorem, but kind of we'll learn more about infinitary logic and properties and working with it. And then prove, I don't think we're going to be able to prove all these equivalences. Some are hard. And defining the techniques for them will require more than 3 classes, but we're going to be able to prove, I think, quite a few of them. and then maybe some implications one way and not the other, but we can see how it goes. Again, it'd be useful if I know how fast I can go later, because to see how many of these proofs we can do. But yeah, that's the objective, kind of, to have an objective towards the end of the class. Are there any questions?
The question about this theory, how many part of this is restricted to countable structure, and which part of it can be extended to arbitrary structure? Arbitrary.
Okay, so this you can do for countables, for arbitraries. This one. Okay, these two are equivalent up to are no, not really. Okay, so this one and this one not, because you cannot talk about the space of structures in, if they are uncountable, then the space of structures get more complicated, so that's more difficult. So I mean, maybe there is some way of talking about uncountable structures in that setting, but it's not that standard. So not those two. This one, you can do a version which will play along with the others. So the Scott sentence for a structure in this way, it wouldn't be one that identifies A up to isomorphism, but one that identifies A up to what is called, I don't know, back and forth equivalence, or L omega up to L infinitary omega equivalence. So instead of isomorphism, you look at this different kind of equivalence, and you find sentences that identify A up to this equivalence. Then there you will get something where you can play along and have a theorem that says you're isomorphic to this and this. So I could mention that when I mentioned the back and forth property, I can mention something about this and what extends to the uncountable case.
Thank you. Do we have other questions?
I have a question. So, do you know how many structures has isomorphism functions with Bayer class 0?
Bayer class 0?
Yeah, how many countable structures has such property?
I would guess continuum, many.
Really? Okay. How many linear orders? How many linear order structures has Bayer class 0?
Oh, linear orderings. No, the rationals.
Only the rationals.
Only the rationals. So yeah, so it's interesting. So for linear orderings, you can see which ones have Scott rank 1, meaning isomorphism function that is that, and then it's only the rationals. If you allow parameters in your linear ordering, well, I guess you can have the rationals with parameters. You can have consecutive elements. For Bayer class 1, it gets interesting because then there's a few more, but not too many more. Like you have integers, you can omega star, but not a lot.
Finite many? Okay.
Yes. And then, but then when you go to Bayer class 2, then you get continuum.
Lots of. Okay.
In the case of linear ordering. Yeah.
So another question is, if you start, have you looked at the Year-Shov hierarchy? For example, with the Bayer class 1, then there are substructures of Year-Shov hierarchy. So do you have any characterization like this, like your theorem?
I haven't looked at it. What I'm thinking is whether you will get something new. I'm not sure you will get something new. Okay. But maybe you would. I wonder if that's. Yeah, no.
Okay. Okay, thanks.
Oh, how does computability theory come into the scene? Right. So this theorem, the way it is, doesn't mention computability theory that much. So this one here, this notion here is just a translation only for this talk about a computability notion called delta alpha computability categorical, which measures the computational complexity of these isomorphisms. And then this means that you need alpha jumps roughly to compute the isomorphism. So this one has a computability notion. And the way you know how to prove it is also using computability. So the connection between these the isomorphisms, yeah, this is the computability. And the Scott ranks uses that. The other ones, and not that much. I guess there are some things you can effectivize. But essentially what happens is so many notions that are studied in computable structure theory, they end up needing kind of to understand the Scott rank of the structure. But the Scott rank itself is not a computability notion, it's a purely structural notion that doesn't need computability. So it's a tool that shows it appears quite a bit in computable structures, this Scott rank. By itself, it doesn't need, it's not a computability notion. So some of its equivalents you can refine and have effective versions of its equivalences. I don't think I'll do it in this course, but yes, but we can look at computable infinitary formulas instead of formulas of arbitrary complexity, and there is more coming in. Oh, why is, it's another question, why is in the formula sigma 0? It is sigma 0 in the example here on the rationals. What's happening there? This formula here is sigma 0 also. It's both. I mean, if you're sigma 0, you're sigma 1. And that's just a technicality that we don't consider the case 0 because the case 0 doesn't work very well. Let's go back. Oh, okay. So I should have said here this alpha. Here equal to 1. Yeah, for everything to work with correctly, we look at ranks 1 and above. In this case, the case when you have sigma 0 there to differentiate it with the case when you have sigma 1, I don't think it's a robust notion that you get anymore, but I will say that it's still something that could be interesting to see what happens. Like for structures like the rational, where you can do with sigma 0 instead of sigma 1, whether that buys you anything in terms of complexity or something, I think that's an interesting question to ask. I know in some cases it does, but I don't think I have a clear theorem of what happens when you have definitions to be sigma 0. But yeah, good codes, CZC. Is there a way of constructing a structure of higher rank from structures of lowest rank? Yes, and we'll be, I don't know if we'll be doing that, but yes, so in many cases you can put together structures of lower ranks to build ones of higher rank. We're gonna be looking at structures like ordinals, they have very high rank and these kind of things. So yes, the answer is yes. So for instance, in the case of linear orderings, if you put omega linear orderings together on smaller rank, you're probably going to get something of a rank that is +1 or +2 of the previous ones.
Do we have more questions? If there's no more questions, do we know that we also still have a review section in the afternoon, and people are welcome to discuss, and we can hear your feedback if the talk the step, I mean the rhythm is good. And
Cool. Yes, I like some feedback. So if you can write something, I can see when I wake up tomorrow morning.
Yes, and yes, then we meet tomorrow in the morning.
We meet tomorrow at 8 Shanghai time, and we'll be working on infinitary logic. Yeah.
So that concludes today's lectures. Let's thanks to Professor Antonio.
Thank you, guys. All right. See you guys tomorrow.